Gravitation, basically, let's start straight away to the law. What does it say? Here you have the equation F equals to Gm1 m2 over r squared. Okay, basically this is saying that if I have two masses, regardless of the shape, let's say I have a mass here, I have a mass here. This large body, we will treat the mass as if it is coming from one point. Okay, so it's like a point mass. We know that the mass is distributed over the body, but let's just treat the mass from the center. So we take the center of mass here. Here and here, we will draw a line, the distance measuring here, this is the R. Now, Newton says, when you have mass, like when you have a body, you have mass, m1, m2. And he says that whenever you put two mass together, right, they will attract each other. That means by nature, if you have two masses, they will exert a force of attraction. This will be attracted to here, this will be attracted to here by the same magnitude. Now, mind the word, same magnitude of force is acting on two bodies. How do you label the force? Draw the line joining them. The force is always parallel to the line like this. Okay? Now, he says that this is the force and it can be calculated by using this formula here. And notice that this formula depends on the product of the masses. Whenever one mass increases, it will increase the force value. The product, this increase, it will increase. This increase, it will increase. And also it depends on R squared. R squared, it means it has a larger effect on the distance. If this distance twice, this one become 4. If this R increased by 2 times, this will decrease by 4 times. So it has a larger weight to the distance. Okay? Now, from here, what is this G? This G, if I rearrange my formula, I get G equals to F times R squared over M1, M2. This is a constant value where it is given 6.67 into 10 minus 11. What does it mean? This constant value, just to give you an idea of what is this value mean, is that, let's say we let our M1 become 1, M2 become 1 kg. Okay? And the R also become 1 meter, all in standard unit, right? If everything become 1, 1, 1, 1, then we see the G is equal to F. That means if you take 1 kg, separated by 1 meter, how much is the force pulling them? This much. That is what the constant means. Okay? If I take 1 kg separated by 1 meter, how much force pulling them? Newton says this is a fixed value. It's going to be very small, 6.67 times 10 minus 11. 6.67 times 10 minus 11. Newton is pulling this too. This is basically what the constant means. And this constant applied to everywhere in the universe, every corner of the universe, from small scale to large scale. This is always true. Okay? Now, then if I have 5 kg, then you will put in the equation here. If the distance is 5 meters, you will put in the equation here. That's why we get this one. Based on how much the two masses and the distance, we get the force total pulling them. Now, looking at this, Newton's law, right? That means, does it mean that every single body will have force of attraction? Yes, technically, yes. You sitting beside your friend, you will have gravitational pull. But How large? You can calculate what is your mass, what is your friend's mass, how far you are apart. You can calculate the pull between you guys. But the value is going to be very small because right beneath you is the Earth. And the Earth has a very large mass. It almost neglects every masses on the Earth, all the other objects. Okay, but technically you will have experienced gravitational forces. Now, here, this is you. This is the Earth. Again, you and the Earth, two bodies. This is body 1 and 1. This is body 2 and 2. Now, your center of gravity, the Earth's center of gravity, draw a line, that's the R. And then our force of attraction, and here, this one. You and the Earth experience the same force. How much the force is pulling you, which is your weight, if you are 60 kg, your weight is 600 Newton. This is basically this one. Is basically this one. 600, your weight is the gravitational force pulling you towards the Earth. That means if you are pulled by 600 Newton, that means the Earth is also pulled by you 600 Newton. Okay, something to take note is that the point is what? The point is that the force is always the same magnitude on two bodies. Now, then comes the question again. If the two forces, same magnitude, act on the two bodies, how come I fall to the Earth and not the Earth fall towards me? How come I fall towards the Earth, but not the Earth fall towards me? Because here you have F. F equals to M1A. F and A. A equals to F over M1. This is acceleration of the Earth. This is U. F equals to M2A. A equals to F over M2. This is acceleration of the body. The Earth mass being very large. You both experience the same F. This is very large, so the acceleration of the Earth is very small. Your acceleration is relatively greater than this one. That's why you accelerate towards it and not the Earth accelerate towards you. The answer lies in the mass of the body. Okay? So again, the force of gravity is the same for two bodies. But the effect of the force is not the same. The effect, that means the acceleration. The force creates greater acceleration on you than it does on the Earth because of the mass. All right. Now, gravitational force is the nature of it is a long-range force. If the question asks you, describe the nature of gravitational force, you need to be able to describe it. First, it is a long-range force. It can stretch to very far. The sun can attract all the 8 planets very far. This is different from the force in an atom. The atom, this is the nucleus. In the nucleus, you have proton and neutron. The force is holding these two together. What we call this force, this is a strong nuclear force. This strong nuclear force is very, very strong force, but it is a very short range force. The moment I bring the neutron further a bit, this force will disappear. This is what happened inside the nucleus of an atom. Okay? This one is in another chapter you have. But just to compare, the strong nuclear force, the gravitational force, they are the fundamental forces of the universe. Okay? So this is short range, strong force, but this is long range. The first one, property here. Number 2 is that it is always attractive. It is never a repulsion force. But the strong nuclear force, the strong nuclear is also attractive. Example of a repulsion forces like magnetic force. It can be repulsion forces. And number 3, third characteristics, third property is that it acts regardless of medium. What is the medium between the two bodies? They don't care. They just act the forces. All right, now let's come back to this one. So we know that this F, previously we did F equals to mg, right? Now you use the Newton's law of gravitation. This is gmm over r squared equals to mg. Be careful with the mass. Huh? Whose mass is this one? The Earth, m1. Whose mass is this one? My mass. Whose mass is this mg? This is the person's mass. The force acting on a person. So this is the person's mass. When I cancel this with this one, the g, I get gm over r squared equals to g. The gravitational acceleration is the constant times whose mass is this? This is the Earth's mass. Okay, so I will write here, this is the gravitational field strength of the Earth. This is the mass of the Earth. And this r square will be the from center to here. Please take note of this. This is the derivation of gravitational field strength. This is in your syllabus. They will ask the derivation. Okay. Gravitational field strength equals to gm over r squared. See, this is fixed. This mass of Earth, as long as it is Earth, is fixed. So g depends on r squared. R squared is distance between me and the center of the Earth. Previously, we learned that the g value is 9.81. What is the radius here? Can we calculate this? How do we actually get 9.81? Okay, we can actually calculate using the formula. G 6.67 times 10 minus 11 times mass of Earth. What is the mass of Earth? Close to 5.97 into 1024 kilogram. Be careful when you use the formula, it is always in SI unit. Over r squared. What is r squared? R squared is the distance between you and the Earth. So here's the Earth. You are very close to the Earth. Like you're standing on the surface, right? What is the radius from the center of mass, of your center of mass, here to your feet? A few meters, 1 meter or 2. Okay, 1 point something. Here, 1 point something meter, 1.2 meter. How large is the radius of the Earth? This is 6,400 kilometers. You stand here, 1.2 meter. Compare with the radius of the Earth, 6,400. Is this 1.2 going to make a difference? No. So, if it's not going to make a difference, we will ignore it. I just take 6,400. Here, the gravitational field strength at this point, G of the Earth at this point, let's call it point A, is going to be R. I will change this R to capital R, stands for the radius of the planet. Again, why we take R? We ignore the altitude here because it's too small already. So here I put 6400. Again, it's km. So times 10 power of 3. And then don't forget your square. You calculate this. We are calculating the gravitational field strength. At this point, we get this one very close to 9.81 ms minus 2. And that is where we get our 9.81. It is called gravitational acceleration. Why we call it gravitational acceleration? Because this F is producing the acceleration. This acceleration is due to the gravity. So we call it gravitational acceleration. 9.81 at point E. Now, is this value fixed? In all the examples, all the calculations we did in O level, we always take the same value because we assume every single calculation is close to the Earth, where the distance doesn't make any difference. How close to the Earth and how far should it be to have an effect on this one? Again, you can see from the formula, right? This one, when this one increase, this one is going to drop. How much this one increase, this one will start dropping. When your altitude from the Earth is 10 km. Is 10 km high? Very high. 1 km from here to Lido market. Bring it vertical. 1 km. 10 km. The highest waterfall on the Earth, just 9 km. 10 km. Very good. Compared to the radius of the Earth, 6400, nothing. Again, at 10 km altitude, what is your G? Again, 9.81. No difference. 100 km, add another 100 km vertically upward. What is your G over here? 100 from the surface compared with 6,400 km, also nothing. Still 9.81. Very close to 9.81. Stretch this one so far until 1,000 kilometers. Now we are talking about 1/6 of the radius. And here you will start to see the G will start to drop below 9.81. Okay, so that means this calculation only apply in planets, satellites, orbits, in a large scale, where you have a significant change in the altitude. Okay, so like the calculation of a satellite that is 20200 kilometers above the surface of the Earth. Can you find the G? Okay, try find the G. What is the G at this altitude? R. Okay, everybody calculate. 6.67 times 10 minus 11. Mass of the Earth, 24. Radius. Okay, what is the radius? From the center of the Earth. So you want to take the radius of the Earth, 6400 plus 20200 km, that is in km. So times 1000 and then a factor of 2. Yeah, you get 0.56, 0.56 meter per second square. So small. At surface, how large? 9.81. This reduced down to 0 because this is so far away. That is the satellite orbit. Okay, so this part is for the gravitational acceleration. Now, let me clear this one. So if you stay here, if you are here, let's say you're on a satellite, 80 kg. What is your weight? Your weight changes. Your weight is no longer times 10. Your weight is times 0.5. Half. 40 Newton. Okay, so you weigh less when you go up. You continue go out of the gravitational field, then this one will be 0 Newton, the weight. Okay, is this still in the gravitational field? Yes, this is still, the satellite is still in the gravitational field. How do you know? Because there are still gravitational acceleration of 0.56. And one of the reasons why it can go in circle, like orbit, because it is still in the field. Now, graph, again, very important, graph of G against distance. I will put here R, 2R, 3R. R means at the radius of the Earth. Okay, here's the, here to here is R. We know that at the surface is 9.81. Let's draw here, 9.81. This one. The question likes to ask, what is the G at 2R? They always use R instead of giving you the values. 2R, 3R, 2.5R. Okay, what is the G at 2R? All right, then how do you calculate? Okay, try to calculate. What is the G at 2R? if the mass is not given. Okay, so at surface, the G is 9.81. And what is the G at 2R? If you don't know the mass of the planet. At surface, G equals to Gm over R squared. Here, this is a constant, so G is proportional to R squared. What is G? 9.81 equal 1 over R squared, equation 1. At 2R, again we use G equals to proportional to 1 over R squared. Okay. This G I want to find, right? So I make it G dash equal to 1 over, this is 2R squared like this. Then this is my equation 2. Okay. What I'm doing here, my general formula is G equals to Gm over R squared. That's my general formula, right? So at the surface, this is 9.81. This will be the capital R. Because it's surface, radius is R. This is just a constant, we can just drop it. Because later we will find ratio, it will cancel out. That's the equation 1. At 2R, again, we sub into this one. At 2R, G is going to be different. So I will just put a G dash here. The R is 2R here. Okay, then equation 2 over 1. 2 divided by 1. G dash over 9.81. So this is 1 over squared. 4R squared divided by 1 over R squared. Here, G dash 1 over 4R squared times R squared over 1. Okay. Cancel, cancel. This is 1 over 4. So G equals to 9.81 times 1 over 4. Okay, so a factor of 4. At 2R, my G become 1/4. Right? So if this R is 2, the square here, factor of 2, decrease by 4. Sorry, not decrease, it's a factor of 4. If it's 3R, you have a square, this 19. So you already know the value. Here, 1419. Okay, 2.45. So down here, this is almost 10, this is 5, 2.45 here. Here, somewhere, okay, I'll just draw it in. You will see this is a very steep graph. At first, it dropped very steep. Then, we flatten this. This relation, what do we call this relation? Here, G is proportional to 1 over R squared. This is the relation of the graph. This is called inverse square law. You have the directly proportional graph, you have inversely proportional, you have the inverse square law. Okay, so 2 times, 3 times, 4 times, this one drops. What about here? What about inside the Earth? I know already my G, as I go out, it's going to decrease. Okay, that one settled. If I go inside, what happens? If I go inside, let's say I'm here, or maybe I'm halfway here. 1 over 2R. Okay. Now, if I go in here, let's say I'm here at this point, how much of the Earth is pulling me? We draw, you can see I draw a circle here. If I'm here, I can say this much of the Earth is pulling me to the center. Not outside here, because now I'm inside. So I would say this much of the Earth is pulling me. If I go smaller inside, this much of the Earth is pulling me. So I will say that when I go inside, smaller portion of the Earth is pulling me. Smaller portion of the Earth is pulling me. That means the mass is changing. Here, larger mass pulling me. Here, smaller mass pulling me. If I go in, smaller and smaller mass, we say that the effective mass is changing. The effective mass of the Earth. Okay, so I will not go through all the calculations on how to get the graph here, because it will not be asked, just for understanding over here, and also just for the sake of, if they ask concept, you will be able to explain. If I go in, the effective mass will increase. Conversely, if I go out from the center, the effective mass will increase. From here to here, when I go from 0 to the radius, the effective mass increase, the G depend on Gm over R square, right? This mass here increase, this will increase. This one you will get a straight line like this. It turned out to be a directly proportional graph. We can actually do the derivation mathematically, we will get a straight line graph. What the graph is telling you, as you go increasing from center to here. More of the mass of the earth is pulling you. That's why your G will increase. At the maximum, at the surface here, you go out, does the effective mass increase again? No. The effective mass, if it is this big, then this is this big already. I go out, the effective mass is just this big. That's why starting from here, it increases. Because of the distance. Okay, so if I go from center, then the effective mass is more of the earth is pulling me. That's why the G here is gets stronger and stronger, and it peaks at the surface here. So this is your graph, gravitational field strength graph. Okay, now this becomes very interesting. Why? You see here, 0 to R. When I go from surface to center of the earth, my G actually decreases from 9.81 to 0. Have you seen the movie? There's one movie, the Total Recall. Anybody have seen Total Recall? There's one scene that they use the earth, they make an elevator. They call the gravity elevator. This is based on this. You see, at the surface, what is your G? 9.81. When you're here, your G is 9.81. Where is it acting? Towards the center. Acceleration, ma? Acceleration is pulling you towards the center. Here, I drop you. You fall with an acceleration 9.81 towards the center. As you fall, your velocity will increase because you have acceleration. As you fall, the acceleration 9.81 decreases 8, 7, 6, 5, 4, 3, 2, 1, 0. At the center of the earth, your acceleration is 0. You fall to the center here, your acceleration, G now is 0. That means you have reached the maximum speed at the center of the earth. Okay? From here, your V is 0. Go down, you increase your V until the maximum at the center. Because at the center, your acceleration is now 0. Now, here's the thing. You continue to fall because at this point, you reach maximum velocity. Even though the acceleration is 0, you continue to move. You don't just like suddenly stop like that. You continue to move starting from here onwards. Now the G becomes a negative acceleration because the acceleration is pointing towards the center of the earth always. So you move here, the G becomes a negative. From here, here, your velocity decreases back to 0 over here. Zero to maximum, maximum drop again back to 0 because of the negative acceleration. Then once you reach here, you have 0 speed. The negative acceleration is acting again. So you repeat again, you go back. This is light. Going here, going here, going here, going here, going here, forever. You see your velocity here, V0, V0, V maximum at the center. This looks like what? A pendulum. V0, swing here, V0, in the middle. We have V maximum, like this. This one you go like this. Okay, same thing. What happened here? This one. Okay, the gravitational field strength. All right, so the graph, the derivation, and of course the calculation lah. Okay, the calculation. We'll do some exercise. I actually have one question here. Okay, you try this question before we proceed. Okay, any questions so far on this one? No, huh? Okay, you can take down and try this one. What already? See? .26. The 5.2 between our data. But it's close, but it's also if you will affect the answer. Guys, remember in your calculation, if your final answer is in too significant, remember your working take more than that, because you are dealing with big numbers here. Usually your number is very big, like you can see like factor of 24, all that. So the significant figures is going to affect your final answer. Okay, you want to take as be careful with the significant lah. If you want to take 2 SF in the working, maybe you take 3 or more than that, 3 or 4. Finally, you need 2. Okay, so when you deal with large numbers, it's very easy that your answer will be a bit off than the actual value, unless you take everything all the decimal. Okay, yeah, it's close, Valen. 6 point something, 6.16 times 10 power of 17 is the resultant force. Newton on the x. And here, double. This is fxx, fy, yz, xz and yz. Okay, so acceleration, you just do F equal m, ma. Right, so you've got 2 forces, one is between these 2 bodies, one is between these 2 bodies. If you have at the center, if I want to find the resultant force at the center, then you have these 2 F1 and these 2 F2. Then it will be minus because opposite direction of forces. You get acceleration really well. Okay, guys, a little bit more. Okay, now we have done circular motion and you know gravitation force. Earth moving in circular motion, centripetal force must have to produce this circular motion. Who is the centripetal force? The gravity is the centripetal force. Again, how you label? Join the line, that's the R, this is the F. Same F, and this is given by GMM over R squared. Okay, the big M I will use the mass for central body. Central body. That means any body that is being orbited. This I will call it orbiting body. Okay. Centripetal force is the gravitation. Is there any other forces? Unless you have planet over here, that is going to act the force on this one. So that's going to affect this one. So let's just make all this simple. We will treat that these two is isolated. That means it's like the surrounding, there's no other planet pulling them. Okay. So all the centripetal force is from the gravitational force of the sun. Centripetal force given mv square over r. Whose m is this? The mass of the earth. Here. Its m is the mass of the earth. V is the linear velocity of the earth. And then r, of course, is the radius. Equate them, we get GMM over r squared equal mv squared over r. Cancel, cancel. We got GM equals to, I bring this one over here. V squared R. From here, we will branch into two steps. First, GM equal V squared R. We know that this V from the centripetal, the linear velocity is R omega. Okay. So if you forgot already, you have to go and look back. This V equals to R omega. V squared equals to R squared omega squared. Put it inside this one. So GM equals to R squared omega squared into R. So this is R cubed omega squared. There goes your first equation. This is with the angular velocity inside. Whenever they ask for angular velocity, or they give you angular velocity, then use then you use this one. The second one, GM equals V squared R. Okay. The second one, your V again, the V, linear velocity, V equals to, is there any other formula for V? Except the R omega. Velocity, we also know distance over time. For the circular motion, distance will be the distance traveled at the circumference, this will be 2 pi r. Time. The time that you go one circle. Time for one cycle, that is period. So here I will write period, T. So V equals to 2 pi r period, over period. Okay. Again, we want to put inside here. We want to square it first. V squared is 2 pi r squared over T. That is 4 pi squared r squared over T squared. Okay. And 4 pi squared r cubed over T squared GM. We group all the constant value to the left hand side. 4 pi squared is a constant. Put it on the left hand side. I will have GM over 4 pi squared equals to R cubed over T squared. There you have your second one. Notice your left hand side is a constant value. This is distance and period. This is distance and angular velocity. These two formulas you need to know. The derivation, do you need to know? Yes. The derivation you need to know. How I get this? How I get this? They will ask you. Okay. Right. Now, okay, formula we know. What does this mean? What I'm doing here? Okay, let's see. Let's take this one. Okay, you can take this or this one. Let's say I take this one. See what this means. GM, I will write it here. Equal R cubed over T squared. Okay. So back to our diagram. What is R cubed? R is the distance of the Earth from the Sun. R. Okay. Sometimes they call this radius. They call it mean distance. They're all the same thing. Radius, mean distance. That's the R. Okay, look at the diagram. That formula is for this diagram. R is here. What is the T? T is period of whose period? The orbiting body. This one. Period is time for one cycle. What is the time for one cycle? The Earth goes around the Sun 1 year, 365 days. Now, that means if you take the distance between the Earth and the Sun, you cube it, you divide by the square of the Earth period, what do you get? You will get a constant value. You will get a value, a fixed value. That also means, okay, stick with me, that also means I take another planet, right? I take the Mars. The Mars also orbit the same central body, right? The same central body. This is the orbiting body. If I take the distance of the Mars and the Sun, again you have R. Let's call this R2. And then the period of the Mars, T2. Again, you take the cube of the Mars divided by the square of the period. You do it for the Mars, you do it for the Earth. They are the same value. This one, you cube, divide by square of this, is equal to this one, you cube, divided by the period of the Earth. So I will write R1 over T1 squared. This is for the Earth, right? Is equal to R2 cube over T2 squared. This is for the mass. They are the same. Surprisingly, they are the same. You do it for every single planet, provided all the planets orbit the same central body, the Sun. It cannot be a different central body. This will always be true. Okay? You do it for the Earth, you do it for the Mars, you do it for Venus, Jupiter, Uranus. All they have the same value. So R1 over T1, R2 over T2, R3 over T3, R4 over T4. You get this. It's because of this one that I can calculate the period, the distance of every single planet, provided I know Earth. I already know Earth. I know the distance of the Earth with the Sun, the period of the Earth. I already know. All I need to know is what planet, Mars. I want to find the distance. If I know the period, then I can find this. Okay. Any question from this part? This part, okay? The good thing is this formula, is it limited to Sun and Earth and the 9 planets, the 8 planets? Answer is that this is applicable to every system as long as you have a central body and you have an orbiting body. This applies again. Example, the middle is Earth. You have a satellite. Satellite 1, you have satellite 2. Can I apply that one? Yes. What is the R2, T2, R1, T1? Again, you can apply. What's the difference between these two? It's just the central body is different. Central body is different. But then this one still applies. Okay? So, using this one, you can calculate what's the period of this, what's the mean distance of this one. I can apply to Moon and the Earth, Jupiter and Jupiter's moon, any planet with the moon, anything orbiting around it, nucleus and electrons, all of them, any orbital system. Okay, that is right. So the 3 important formulas that you will always see: this one, and this one. Okay, you will always see. Same like this one. We do like R3 and angular speed. You take this one of the Earth will be the same as of the Mars. Okay, this one will be the same as this one. So I can write another one. R1 3 W1 equal R2 3 W2. Yeah. So my formula, the gm over 4 pi squared. This one. Whose m in this? The mass of the sun. This is the mass of the sun in this example. Or should I say the mass of the central body? Mass of central body. That means if I bring this over here, 4 pi over here, gm 4 pi r cubed over t squared, g bring over here, gt squared. Whose mass is this? The mass of a central body. That means in any orbit, you can find the mass of the central body using this formula. Okay? Whose mass? Central body mass. You need to know the mean distance of who is the orbiting one and the period of the orbiting one. Then you can find the central body mass. For this one, I can find the mass of the sun. For the earth, I can find the mass of the earth using this one. So I would say the gravitation questions is always this form. The rest is just concept. Okay? They ask you like concept, that means like they ask you, okay, if the distance increase, then what happened to the force? Something like that. Relationships. Okay? For calculation, you will always see this form. Right. Take down this one. And we'll try a question. Only the one I circle, guys. Only do the one I circle.